Okay, so this is the first video, which I'm going to make a series of videos to replace the lecture on Wednesday, November 29th. And this is the first one of these. The goal of this first video is just to visualize space-time data. So on Monday's lecture, we talked about the format of space-time data, and I think a useful way of thinking about space-time data is to think of the stacking the data as snapshots in time. So any snapshot in time captures the spatial nature of the data, and then we think of the data advancing in time as we move our way up the stack. We are going to be looking in R, and there is this spacetime.r script, which will be posted on Canvas. And the first goal, as I said, is just to visualize this data. So just sweep these entirely. Okay, so I am actually basically taking this directly from this book, Spatiotemporal Statistics with R by Weichel, Zavet, Mangione, and Cressy. This is a book that is free to download. And if you go to this URL here, you can download this book. I am basically following Lab 2.2 in this book, and a lot of it is directly cut and pasted. So it requires you to install some packages. If you don't have all these packages yet, in particular, we're going to be using a package that is, I believe, only exists on GitHub, which has some data sets in it. So I've already installed those packages. I'm going to load in all of these libraries. And we are going to look at a data set in this package called NOAA DF1990. So I've loaded that data set in. You can see that this is a data frame, so think of it just as a matrix with different types of entries. Here is the first few lines of it. Julian is a way of storing dates, so that each Julian advance is an advance of 1 day. But we have the date code here. We've got data starting in 1990. I think it runs through 1993. This ID is the identifier of a particular weather station. Z is what we're going to is the data variable of interest, and we actually have several different variables in here. We got, I guess I don't have this here. Let me just say unique. NOAA. ROC, and you can see that there are different weather variables stored in this data set. We've got Tmax, which is the maximum temperature of the day, the minimum temperature of the day. I don't remember what TDP is. We could look at it, or we've got precip. We're going to be looking at temperature because it's kind of nice. Precipitation is particularly messy because it's got a whole bunch of zeros. Only takes on positive values, and so it's pretty tricky to model statistically. Temperature is much easier. So what this line, starting in line 29 through 32, is going to do is, you can see it's going to filter this data. It's going to extract only the Tmax variables. It's going to extract only the months from May to September, and it's going to extract just for the year 1993. So basically, we're going to take one summer's temperatures for all of these stations. Oh, I should have, I wanted to show you one thing first before I did that. Notice that the original data set is huge because, of course, it's got these number of variables, but more importantly, because it's got data from a whole bunch of stations, and every day you end up with 700,000 observations. And so this just illustrates that space-time data is very large, And so that's one of the things we have to think very carefully about when we're modeling it statistically. Okay, so jumping again down to line 29, I've run this filter. This Tmax variable that we've created looks about the same in terms of how it's structured, but of course it's much smaller because we have subset on just one variable, 1 year, and just the summer months. So even so, we've still got 20,000 observations. So you can imagine we've got, because we're going from May to September, we've got 153 days. So our stack is 153. And then if I divide this number by 153, we see that we've got, roughly 133 stations. Some of these, not all stations report each day. And so we don't have a nice, the same size vector of spatial observations for each day, but it doesn't vary too much if you investigate this. Line 35 is just something that is going to allow us to work with this data more easily. What we're going to do is we're going to take our Julian date, we're going to subtract off 728049, which of course is going to make the first day, day 1, the second day, day 2, etc. We actually have this already stored in our data as something called day, but the script that I copied had that stored as T. And so you can see now we've created we've just added this column T on there. And then what you'll see is, in this script, there's some stuff calling for variable T. Okay, so we've got a whole bunch of data. We'd like to just explore it, get an idea of what this thing looks like. And really what we can do is we can explore the data spatially. We can explore the data temporally, and then we can try and explore both space and time at the same time. So starting at line 37, we're going to explore the data spatially. And so what's going to happen here is we're going to extract 3 days. We're going to extract day 1, that'd be May 1st, day 15, and day 30, and we're just going to make spatial maps of this. So this is treating the data as if it's not space-time. It's just treating each individual layer, each individual day as an individual data set. And let's see what it looks like spatially. So line 38 is going to subset so that our variable that we just created T is either day 1, day 15, or day 30. And then line 39 down through line 51 is making a plot, and we're using the ggplot. I haven't talked about ggplot in class. Most of you are probably more familiar with ggplot than I am, but it's a nice way of doing plots and kind of allows you to build layers and things. And this is really extracted just verbatim from the from lab 2.2 in the book. But it's going to make points at the lat mon of each of our stations. It's going to attach it's going to basically just color each point by the temperature at the station. So running that creates the object, and then to plot it, I just do print, and we see that here we've got May 1st, we've got May 15th, and we've got May 30th. And what we see is there's a clear indication that temperatures exhibit spatial correlation. And on May 1st, we've got some colder stations here, down in the high 40s perhaps. Up in Minnesota and the Dakotas, and then, warmer as we move to the southeast. May 15th, we've got some very warm days, in the 90s down here in Texas, and then May 30th, we've got some very high temperatures down here in Mississippi and Alabama. So we're not surprised by this. We would imagine that temperature data would show a spatial signal. we could investigate this spatially. We could fit variograms to any one of these days. We could combine across days to get a spatial signature. So we know how to explore the spatial nature of the data because we've been doing that. We did that back in the geostatistics section of the class. This just shows that I already talked about this, but not every day has the same number of stations reporting. Some days have 133, some days have 132, just as different stations, have missing measurements. That's not too critical to us as we're exploring this data, but it's something to put in the back of our mind that if we were to think of one of the things that we talked about in the lecture on Monday was a separable structure and structuring the big covariance matrix of all your data in a Kronecker form. And here we'd have to work with that Kronecker form because not each of our blocks would have the same number of stations. And so we'd have to consider that as we're building our model. Okay, so we've explored things spatially. We see that the data has spatial behavior. We're unsurprised by that. Let's look at it temporally. So what's going to happen here in line 60 is it just gives the unique station IDs. You'll recall from when we plotted, or each station has an identifier number. So UIDs is just getting the list of those. And then line 61 is going to extract a random sample of 10 of those. And then line 62 is just going to filter our Tmax data frame by those samples. So we're making a smaller data set, which only has data from these 10 stations. And then again, we're going to use ggplot here. And basically what this is going to do is it's going to make a time series plot for each of these 10 stations. So here we have, we plot that, and here are our time series. And we could look and see where each of these stations are, but what we see, here's a station that clearly starts off colder than some of the others. We're seeing that, a general up and then down pattern. Of course, that's seasonality. We're starting in May, we're going through July and August, and we're ending in September. And so we're seeing that seasonal behavior pretty clearly. Some of the data sets show less seasonal behavior. So there's seasonality here that we might want to try and remove with some sort of mean structure. That mean structure would probably have to vary over space. Seasonality in Minnesota is not like seasonality in Alabama. There probably is also short-term dependence. So if we, for instance, if we look here, we're seeing probably a bunch of observations that are high. We're seeing a few observations that were low. If after we account for seasonality, we're seeing some temporal dependence still. And so to account for that temporal dependence, that's where we would build a time series model. We'd want to capture that with an AR1 or an ARMA model that somehow accounts for that autocorrelation structure. I looked at the autocorrelation structure a little bit. This was something that is not in that lab, but is pretty straightforward to do. I'm going to look at just this first station. So that's going to be stored in station 1. I'm going to just smooth that data. I'm using a moving window with a pretty wide moving average, not moving average in terms of time series model, but just take the average of a window of width 31 and apply it to this data. I create the smooth data, and then I can show you, here is that stations data. Here is the seasonal smoother that gets applied to it. And then I can look at the residuals. So just looking at this data set minus that pretty crudely estimated seasonal behavior. And so here are the residuals. And then the question would be, after we remove seasonality, are we seeing some indication of temporal dependence? If we look at the autocorrelation function, we see that, not surprisingly, there still is temporal dependence. So if today is warmer than what we would expect seasonally, tomorrow is likely to be warmer. And so we're seeing some temporal dependence up to, lag 3 or 4. There might be some even indication of having some negative dependence at a lag of 8 or 9. Okay, so a model for this data would want to account for, really all of this sort of thing. The modeler would have to ask, how do I want to build seasonality in? How do I want to capture temporal dependence in? How do I want to capture spatial dependence in? But another question then is, could I use a separable model, or do I need to do something that's non-separable? And so perhaps the best way of doing that is to build an animation. So remember what we said was, we can think of stacking our data in time. Each one is a snapshot. Well, if we build an animation where we loop through each of those snapshots, we can see how the data evolves through time. So we're really capturing that space-time nature. And so this is pretty slick. I haven't done an animation before, but copying their code was easy enough. And so what this section does is, it just, for a given day tau, it builds a map of the temperatures. And then here we're creating that animation. We built in a library that was animation, and so this gen m, well, actually this is just going to loop through. It says for t, in the hopefully this is going to work. Oh yeah, I've got lim t right here. So it's going to start at the first time and go through the end time, and it's going to make a plot. We're going to store that in gen nm, and then this options is just saying that it's going to put 2.2 seconds between the frames, and then this save HTML creates an HTML file of this animation. So if we run this, it takes a minute because it's building all of those all of those layers. And then here we are. Actually, I'm going to need to give me just a second here to show you where my screen automatically bounced to. Okay, so RStudio actually bounced me immediately to my browser, and I'm in that animation file. You see noaanim.html. This was the file name that was created. I can hit play, and what we see is we're evolving by day these temperatures. And I think what you can kind of see is that we see temperatures move from west to east, from left to right. It's not a slam dunk, but we're seeing some, to my eye, we're seeing some motion moving from left to right. And so what that would indicate to me is that to best capture this dependence in the data, we would want to use a non-separable covariance structure, because a separable covariance structure is fully symmetric. Remember that definition of fully symmetric. And so we would think that if things are moving from left to right, from west to east, then the covariance between a station here in the west on day t and a station here in the east on day t+1 would be higher than the covariance on a station here in the east on day t and a station west on day t+1, because t+1 is a day later. We would think that things would move from west to east. Okay, so what we've done in this little video is we tried to visualize space-time data, and it's a challenging thing because we want to look at it spatially, we want to look at it temporally, we want to put it together in a sensible way, and we've looked at some pretty cool tools to do that. All right, I will be posting more videos soon.